In the previous video, we defined Fourier series and we calculated an example of a Fourier series. And in this video, we're going to do a couple more examples of calculating Fourier series. And we'll also see that when a function is either odd or even, it makes calculating the Fourier series easier. So this example is compute the Fourier series for f of x, which is -1 if x is between -pi and 0, and 1 if x is between 0 and pi. So let's draw a picture of what this looks like first. So here's -pi, here's 0, here's pi. It's -1 between -pi and 0, and it's 1 between 0 and pi. So first, we're going to need the an's and the bn's. Let's just write down the formula. Well, an is, now what's my t in this case? T is again pi, just as in the previous example. So it's 1 over pi times the integral from -pi to pi of f of x times cosine of n pi x over pi, so that's nx, dx. Now, we could calculate this, but there's an important fact about f of x. This function, is this an odd function, even function, or neither? It's an odd function because it has the 180-degree symmetry, right? When you plug in x and -x, you get negatives of each other. So if you plug in the value of x here, you get 1. And if you plug in -x, you get -1. Because, so f is odd because f of -x is equal to negative f of x. So since it's odd, okay, what kind of function is f of x times cosine nx? Well, cosine nx is an even function. Right? So this is an odd function times an even function is an odd function. And we know that when we integrate an odd function from -L to L, what do we get? We get 0. So actually the an's are all 0. Okay? And this is, in fact, what you would get if you did it the long way. So if you didn't notice that f was an odd function, then what you would have to do is you would have to split up this integral from -pi to 0 and from 0 to pi. And between -pi to 0, you would use f of x is -1. And then between 0 and pi, you would use that f of x is +1. And you would calculate the integral of negative cosine nx from -pi to pi, and you would have to calculate the integral from 0 to pi of 1 times cosine nx, and when you add them up, you should get 0. But we're using a quick fact that f is odd, and that means that the an's are 0. So we just need to calculate the bn's. So for bn, for this we will have to split up the integral. But actually, let me just write this down. So we have f of x times sine nx. Actually, what's going to happen is that since f is odd, and sine nx is odd, the product of two odd functions is even. That means that the function that we're integrating, this function that we're integrating, this is an even function. Because the product of an odd function and an odd function is even function. And when you have the integral of an even function from negative pi to pi, that's just 2 times the integral from 0 to pi. So I can actually write this as 2 times, well, 2 times 1 over pi is 2 over pi, times the integral from 0 to pi of f of x sine nx. So this is because the function I'm integrating, f of x times sine nx, is an even function. And now I see that x goes from 0 to pi, so what's my f of x? It's just 1, right? I look here. When x is between 0 and pi, my function is 1. So my function here is 1. So I'm integrating sine nx, and n is greater than or equal to 0, so I can divide by n. So this integral is 2 over pi times negative 1 over n cosine nx. Oops. From 0 to pi. So this is going to be negative 2 over pi n times cosine of n pi minus negative 2 over pi n. So that's plus 2 over pi n times cosine of 0, which is 1. And I know that cosine of n pi, that's equal to negative 1 to the n. So I'm going to get 2 over pi n, and then I have this negative 1 here, which I can combine. So I'm going to get, I can actually factor out the 2 over pi n. So I'm going to get negative 1 to the n plus 1 plus 1. Now notice that this can actually simplify a bit more, because if n, let's see, because when this is negative 1, this negative 1 to the n plus 1, when that's negative 1, that's going to add to 1 and give you 0. So let's see, when is negative 1 to the n plus 1 equal to negative 1? That's when n plus 1 is odd. So that's when n is even. Right? So when n is even, n plus 1 is odd, so negative 1 to the n plus 1 is negative 1. So your Bn is going to be 0. So this is equal to 0 if n is even, and if n is odd, well, if n is odd, then n plus 1 is even, so this negative 1 to the n plus 1 is just going to be 1, and then you get 2 here, so you're going to get 4 over pi n. Right? Because this whole thing is going to be 2, and then 2 times the 2 here is going to give you 4. But there's no convenient way to write this out in the Fourier series. So I guess we could have just skipped this part. I mean, when writing the Fourier series, we would write f of x has the expansion, so the a's are 0, right? The an's are all 0, so then you get the sum from n equals 1 to infinity of 2 over pi n times negative 1 to the n plus 1 plus 1. Which it would be easier to write. So if you want to do the sum over the odd numbers, because when it's even, you just get 0. So you could do this. You could do n odd as the index here, and just 4 over pi n, like this. That would also be fine. And notice that when I'm writing the equals here, I'm saying that this series is equal to this, which is true. I'm not saying that f of x is equal to this, right? So this notation is correct. I'm not saying that f of x equals the sum. I'm saying that the thing above here, the Fourier series, is equal to the sum. Or if it makes you, if you prefer, you can also write it like this, but you don't need to. Okay. To just write it in one line. Oh wait, hold on. I'm missing the sine nx, aren't I? So it's sine nx. I mean, I can even write this as 4 over pi times the sum of the odd integers, sum over the odd integers, n odd integers, as of sine nx over n. This makes it easier to see what the Fourier series actually looks like. So it's going to look like, okay, the question didn't ask for this, but if you wanted to write it out, it would be 4 over pi times sine x plus sine 3x over 3 plus sine 5x over 5, etc. So one thing to take away from this is that if your function is odd, then the ANs are 0, because your f of x times cosine nx is going to be an odd times an even function, which is an odd function. Integral is 0 from negative L to L. So we're done with this example, so just note that if f is an odd function, then all the ANs are 0. And something similar can be said about an even function. So we'll do one more example. This time we'll use an even function. So compute the Fourier series of f of x is the absolute value of x between -1 and 1. So the absolute value of x looks like this. From -1 to 1, we see that this is an even function, right? It's symmetric about the y-axis. When you plug in x and negative x, you get the same y value. Okay, so f is even because f of negative x equals f of x. Right, the absolute value of negative x, same as the absolute value of x. Okay. So if you look at the bn's, okay, if you look at the bn's, it's 1 over, well, in this case, my t is 1, right, because x goes from -1 to 1. So I get 1 over 1, that's just 1, times the integral from -1 to 1 of f of x times sine of nx. No, n pi x over 1, which is n pi x, like this. Well, my absolute value of x, that's an even function. Sine of n pi x is an odd function. So when I multiply them, I get an even function. So I'm integrating, oh no, I don't. I get an odd function. Since I'm integrating an odd function from -L to L, I get 0. So the bn's are all 0. So I just have to calculate the ANs. Let's calculate the ANs. That's 1 over 1 times the integral from -1 to 1, absolute value of x times cosine n pi x dx. And now I have an even function times an even function. This is an even function. The product of an even function with an even function is an even function. So when I integrate from negative L to L, that's 2 times the integral from 0 to L. So I can write this as 2 times the integral from 0 to 1. Now when my function is from 0 to 1, okay, what's the absolute value of x simplify to? It's just x, because my x is positive, right? So the absolute value doesn't do anything. So I just get x times cosine n pi x dx. Now I have to calculate this integral. Yeah, if you know the formula for the, if you just happen to remember the formula for the integral of x cosine x, or u cosine u, then you can just use the formula, but I can never remember the formula. So I'm just going to do integration by parts again. So I get u, oh, well now I have this issue where, again, I cannot use n equals 0. So I have to do n equals 0 separately. So a0 is going to be 2 times the integral from 0 to 1 of x times cosine of 0, which is 1. So 2 times the integral from 0 to 1 of x, that's 2 times x squared over 2 from 0 to 1, that gives me 1. Okay, when x is greater than or equal to 1, then to calculate this integral, I can use integration by parts. So I get u equals x dv equals cosine n pi x dx. So v is 1 over n pi sine n pi x. Then du is dx, right? So this integral is going to equal, let's see, 2 times uv, so that's 1 over n pi x sine n pi x from 0 to 1 minus the integral of v du, so I get 1 over n pi here, sine n pi x dx from 0 to 1. And then this is going to give me, well, so when I do this, I'm going to plug in a 1 in my x, right? So I'm going to get 1 times sine of n pi, and we know that sine of n pi is 0. So I'm going to get 0 here, and then when I plug in 0 for x, I'm going to get 0. So I'm just going to get 0, and then minus 1 over n pi times, okay, now I have this integral, so I'm going to get 1 over n pi, and then times negative cosines, I get a plus here, because the minuses cancel, cosine n pi x from 0 to 1. So I get 2 over pi squared n squared cosine n pi minus 1. And the 2 over pi squared n squared is being multiplied by all of that. So I get 2 over pi squared n squared. Then I have negative 1 to the n minus 1. And so my Fourier, so those are my bn's. No, wait, no. Those are the an's when a is greater than or equal to 1. So now I am ready because I have my a0, that's 1. So I get a0 over 2, that's 1/2, plus the sum from n equals 1 to infinity of 2 over pi squared n squared times negative 1 to the n minus 1. And by the way, this, how can we rewrite this? Well, if n is even, then you just get negative 1 to the n is 1, and then 1 minus 1 is 0. So the inside term is 0, right? An is 0. If n is odd, an is just going to be, oh, and I keep forgetting this. I have a cosine nx, cosine n pi x. If n is odd, then the a sub n is negative 1 minus 1, that's negative 2, so I get negative 4 over pi squared n squared. So I can rewrite the Fourier series as 1/2 plus the sum over all odd positive integers of negative 4 over pi squared n squared. I can actually factor out the negative 4 over pi squared. One over n squared cosine n pi x. So I can rewrite it like this also. So this is going to be, I'm just going to write out a few terms. 1/2 minus 4 pi squared, and then cosine pi x plus cosine 3 pi x over 9 plus cosine 5 pi x over 25, etc. And, okay, I'll put parentheses here, even though strictly it's not necessary. So that's what the Fourier series looks like. In this example. And so note that if your function is even, then you don't need to calculate the bn's. Bn's are all 0. Okay, so that was examples of Fourier series. When you have an even function, you don't have to calculate the an's. The an's are all 0. If your function is the, wait, hold on, let me make sure I get this straight. If f is an odd function, then the an's are 0. If f is an even function, then the bn's are 0.